So, first of all, welcome everyone to Coruña. Bienvenidos a Coruña, bienvenidos. And good morning. And we will have this session about emerging technologies and digitalization. The future of transplant is here, where we will explore how AI, digital health, and emerging technology are transforming transplantation. From AI-driven clinical decision-making and digital post-transplant monitoring to advances in ex vivo organ perfusion and preservation. We are privileged to have 3 internationally recognized experts who will share their experience and vision on how these innovations are reshaping the future of the field. I'm honored to co-chair this session with Dr. Fritz Herbert, and he will present the first speaker.
Okay, also on my behalf, welcome to all of you, and thanks for making it here to this very interesting session. And I'm happy to welcome to the podium Doris Segev. Doris Segev, he just told me he's a computer-trained transplant surgeon, which I very much like that idea, but he's much more. I think you've read a lot of his presentations, and I think he has the talent to combine surgical experience and clinical experience with not only data collection, but also data interpretation. He's been doing this for decades, and he is the head of transplant research at the Langone Center in New York. So thank you very much for coming.
Thank you, and thank you for having a session in English. I also very much enjoyed the plenary session that was just in the auditorium. Really interesting stuff happening here in Spain. And thank you to the organizing committee for inviting me here to this incredibly beautiful city and for making the rain stop and giving us some sunshine today. It's really a pleasure to see old friends, new friends, and to talk to you a little bit today about AI. So the title I was given is AI-driven prediction models to improve outcomes in transplantation from big data to clinical decision-making. And I've highlighted the word AI here and the word big data, and I'm going to talk to you a little bit about what's happening in both. I want to start by a reminder that to use data, we need data. In the US, we're quite privileged to have data systems across all of the field of transplantation. We have a registry of anyone who has ever registered for a transplantation and basically everything that happens with them after registration, every organ offer they get, when they refuse, any organ that they accept, their post-transplant outcomes, if their transplant fails, what happens to them after that, et cetera. And then recently we have data across all of the electronic healthcare records as well, and so we can look at very granular things about patients as well. So we can take these registries, link them to other registries, et cetera. And there are efforts like that all over the world. In various countries and across EU, et cetera. And so the more organized we can be in collecting data and collecting high quality granular data, the more we can use these tools. Without the data, we can't use any of these tools. Most of what we've seen in our field of big data to clinical decision making is classified under what I would call supervised learning. What is supervised learning? Supervised learning is when I give the data to the computer and I say, I think these 8 variables are important. Why don't you tell me how much of an impact diabetes has, how much of an impact cardiovascular disease has, how much of an impact donor features have, et cetera. And we use regression models. I'm sure every one of you has read a paper with linear regression, logistic regression, survival regression, et cetera. We use standard supervised models where we tell the computer what to do and the computer does the mathematics. And almost everything in our field has come from this kind of approach. We can use big data and these supervised approaches to look at trends, to look at risk prediction, to evaluate survival benefit, to doing what we call Markov decision process models, and to identify preferred recipients for various organs. I'll give you one example of each just so that you have a flavor of the kind of things you can do. This is a paper that we wrote in JAMA a couple of years ago where we looked at trends in living donor kidney transplantation in the United States by race to see which race groups we were having improvement in live donor transplants and in which race groups we still needed to do a lot of work. And we discovered that 20 years earlier, if you were Black and American, your chances of getting a live donor transplant were half that as if you were white. 20 years later, after making a lot of effort to improve that, things actually got worse. And if you're Black, your rate of getting a live donor transplant is only 1/4 that of being white. So we can look at these trends to say, where are we improving and where are we not doing well and we need more work? We can do risk predictions. So we've looked at living kidney donors and predicting the risks that they will develop kidney failure after kidney donation. We can do survival benefits. So we published this in the New England Journal a few years ago, showing that if you cross HLA barriers in kidney transplantation, you might have more risk than if you had a compatible donor, but actually the survival benefit, meaning doing this operation versus the next best possible thing that we could do for the patient, which is to wait for a compatible organ, the survival benefit of HLA incompatible transplantation was very high. So we can do all sorts of survival benefit modeling. Somebody is given an organ offer. Do you take this organ offer or do you wait for the next best available organ offer? We can take that to a personalized level and do what we call Markov decision process models. These are basically mathematical microsimulations where I say, okay, I have this organ that's available to me. Do I accept this organ? What will my survival look like? Do I say no to this organ and wait? Whatever happens to me for the next best available organ, what will my survival look like? And we actually can use this in our decision making and also in our counseling for a patient. So if I show this to a patient and say, if you say yes to this organ, this is your expected survival. If you say no to this organ, this is your expected survival. It's quite easy for a patient to see, even though maybe something is weird about this organ, it's clearly a good decision for them to make. We can also use these more supervised techniques to say, I have an organ, for example, a steatotic donor liver, and I'm not sure who on my list would be the right candidate for that. And I can look at what we call preferred recipients, where in a preferred recipient, for example, the outcome from a steatotic liver and a non-steatotic liver is the same. So it doesn't matter to them that we're using something with the risk factor of a steatotic liver. In a non-preferred recipient, a steatotic liver will cause tremendous increase in mortality post-transplant. And so these are the patients that wouldn't be great candidates for these steatotic livers. And we can use these mathematical methods for looking at the interaction between donor and recipient factors to identify the people that we think would be the best recipients for that. Now, remember, I also showed you in the title that I was given the title of AI. And when I think of AI or the whole field of machine learning, now I think of an area called unsupervised learning. Remember, in supervised learning, I explained to you that we give the computer, we give the data, and then we say, these are the factors we think are important. We want you to evaluate those factors. In unsupervised learning, we can give the computer huge amounts of data, and we can say, I don't know what's important. You figure out what's important. You look at the numbers, you do the math, you tell me what's important. This became, for example, very, very relevant in the era of COVID, where we were trying to understand things about COVID and transplant patients, but we had no idea where to look. We can give the computer all of this data and let it do some pattern matching and show us what's important clinically that we might not have noticed. When we say AI covers a lot of different areas of computational technology. most of these areas are in risk prediction. So machine learning, neural networks, deep learning, this is all risk prediction. This is all trying to take variables and have the computer figure out how to predict risk in our patients. The other world, which is the world that we hear a lot about with regards to AI, is generative AI, where AI can, for example, create new things, create new language, talk to you, talk to patients, etc. It's very important to remember, as we're moving into the future of all of this unsupervised learning, that these techniques can do things that we cannot do. AI machine learning can process a lot more data, can pattern match better, even better than us, especially with images. For example, people reading CT scans and MRIs have had AI assistance in these readings for many, many years. AI doesn't rely on theory, especially helpful when we don't understand the underlying mechanisms. AI already outperforms clinicians in some cases. AI is improving at incredible speed. So I tell people, whatever I tell you now, in 10 minutes, it will be outdated in the field of AI. And this becomes very relevant when, for example, we're looking at new versions of the large language models, and I'll show you a good example of that. AI can talk to patients when we don't have time to talk to patients. And I bet that if you asked the patients that you take care of, at least half of them, before they came to see you in clinic, asked AI, asked ChatGPT some questions. So not only can AI talk to patients, but it is talking to patients. Remember I told you that to do data, to use data, you need data? Well, if you're going to do AI, you need even more data than if you're going to do the more traditional supervised approaches. And so again, this is a reminder that the more organized we can be, the more comprehensive we can be in gathering data about our patients, the more we can use these techniques. How many people here have heard, by show of hands, have heard the word neural network? How many people recognize that? Leave your hand up if you can explain how a neural network works. Okay, both of you know. So it's why am I telling a group of clinical transplant people how a neural network works? You need to understand just slightly what is under the hood of how these things work so that you have an appreciation for what they can do well and what the real limitations are of these things. So I want to give you a little bit of an explanation. Maybe if I come back next year to some other beautiful location in Spain, there will be 5 people that can explain to me how these neural networks work. Basically, this is a set of mathematical neurons. That's why we call them neural networks. And each neuron is a weighted sum. Remember back in school when you learned mathematics, this was a sum of various things. It's basically all of the inputs, and each input has weights. Why does it have a weight? Because some of the inputs are more important than other inputs. And if you look at this relatively simple neural network, I wrote neural networks like that actually when I was studying computer science in the 1980s. So these have been around for quite some time. But today's neural networks don't have 12 of these mathematical neurons. They have 12 trillion of these mathematical neurons. And if you think about all of the data that can be processed by that, it can get pretty good. How do we train a neural network? This is the basic example. I want the neural network to tell me, is this a picture of a dog or is it a picture of a cat? So I give the dog picture to the neural network, and it has all of these little neurons. And then it gives me an answer, one answer, either dog or cat. If I showed it the picture of a cat and it says cat, then what we do is we go back and we change the weights so that next time it will definitely say cat. We say, okay, this was good, re-emphasize these weights. If it says this was a dog and I showed it a cat, then it goes back and it back propagates new weights so that next time it will know that that's a dog and not a cat. And you do this about 1 trillion times with about 12 trillion mathematical neurons, and it will learn these things, and it will be able to pattern match these things incredibly well. The thing you need to know is that it's just pattern matching, it's not thinking. This AI has never met a dog or a cat. It just has looked at a lot of pictures and it's created those patterns for it. And that's really an important distinction. This becomes even more important when we start to look at large language models and generative AI. Again, I suspect if I say how many people have heard the term large language models, we'd see many hands, and how many people can explain how a large language model works, all of the hands would fall again. So I hope to give you a little bit of insight. Large language model is exactly that neural network, but it's not telling you whether it showed you a dog or a cat. It's creating a sentence, and it's choosing what's the next word that I should say. Kind of like I'm here giving you a lecture, and every word I choose based on the previous words that I said and all of my experience, how much ever that is. Now, if you give a large language model the entire internet, everything Shakespeare has written, everything in PubMed, everything that we know and that we've documented, it can be pretty smart, and it can predict what that next word should be very, very well. Have you ever done this on your phone where you're typing and it tells you what that next word is that you would say? Sometimes we don't want to know what that next word is that we would say. But it's like that, but obviously with a huge amount of data and mathematical power. But it's no different from your phone trying to predict what is the next word that you're going to say. And I need you to remember again that large language models don't actually think. They are the language versions of mathematical predictions. That's all they are. They are nothing more. They do not think, even though they might appear to think because they are talking the way the internet talks. They don't think at all. They don't understand anything. This is why when we have generative AI draw hands, often the hands have 6 fingers or 3 fingers because it doesn't know it's drawing a hand. It doesn't know how many fingers are on a hand. It's not thinking. It's just predicting what would be the next word, what would be the next dot on the image that it's creating. Now, large language models have some functionality. I will leave you with the concept that the simpler the task, the more likely a large language model is to be able to successfully achieve that task. Okay, this was written in the New England Journal about a year ago. Again, as I mentioned, that makes this very outdated. This is ancient publication on large language models from a year ago, but it shows you some of the things that we might be able to do with large language models in our field. We played around with it for the last couple of years. Here's an example. We fed ChatGPT, which is a general large language model, the American Society of Nephrology transplant quizzes. And we fed them to ChatGPT 3.5, 4, and 4V. And these were versions that changed over less than 1 year. And in less than 1 year, ChatGPT went from 42% correct answers to 83% correct answers. And by 83% correct answers, it outperformed all of the fellows that attended the ASN meeting. And so ChatGPT, not trained in transplantation or nephrology, can outperform most people who have been studying transplantation and nephrology for quite some time. But again, it's because it's matching all of these patterns. When things get into the real world, we see some of these things fall apart. ChatGPT can also talk to our patients. We gave it a bunch of questions that patients ask on Reddit, Facebook, etc. And we went to see how good are the responses, how complete are the responses, how safe are the responses. In general, pretty good, pretty complete, pretty safe. Makes us feel a little bit better about our patients talking to ChatGPT, but also makes me want to improve this to create large language models trained specifically on our field, which is what we're doing today. So again, I remind you that there's a lot of things that can be done with these new technologies. I will also tell you that you should consider AI to be a partner. In 5 to 10 years, no one will be practicing medicine without partnership with some of these new AI techniques, so you might as well become as familiar with them as you can. But also remember that the more data that we can gather on our own patients, the more that we can leverage these unsupervised new technologies. And thank you.
we'll do, yeah, please come here. We'll do the discussion at the end. We'll have a lot of time at the end.
Now we have the honor to have here with us Dr. Marcos López Zoyos. He's the head of Immunology Department of the Hospital of Valdecilla in Santander, and he is also the scientific director of the Valdecilla Biomedical Research Institute, where he's the head of the Immunopathology Research Group. So thank you, Marcos López.
Thank you to the organizers for inviting me. First of all, I must be honest, and after Dory speaking, I cannot talk about digital tools. I'm afraid, but you're going to get disappointed, but I would talk about immunology. I would talk about immune tools we can have in the designing of digital tools to post-transplant monitoring, okay? This is my idea. Well, you have this data from the CTS, and you know that the situation has changed in terms of overall survival after 2000. But the idea is that we are very good in the first year after transplantation, but we still have a big space to do better after the 5th year post-transplantation. We still lose our grafts, and we need to improve in this field. And this is why we are all the time talking and looking for immune monitoring, pharma monitoring, whatever monitoring after transplantation. For sure, we know that hypersensitized patients is the main risk or the main problem we have before transplantation, and this is why we have developed allocation systems just to give an idea, opportunity to these patients. And this change in the 2000s when Paul Terasaki started with the humoral theory of transplantation. HLA antibodies for sure have changed a lot in solid organ transplantation, especially in kidney and lung, and the humoral theory changed a lot. But when Juan Carlos and I took this picture with Paul Terasaki in that time, I must tell that in Spain, at least, and in many places in the world, they were measuring HLA antibodies by ELISA, and we didn't know about Luminex. But this theory was there because they were already working with the Luminex. Sorry, I don't know what I did here. Okay, yeah. The point is that humoral rejection and HLA antibodies account for the loss of most of our grafts. But still, there is a number of graft losses that cannot be being explained by HLA antibodies, by humoral rejection, although we are more focused in the long-term outcome and in the role of these antibodies. The thing is that we started, I told you, with the old ELISA. I want to show this slide here because people in the room probably, most of you know them, but the young people doesn't. And the ELISA was the method we were using. Even we were thinking on using a kind of Luminex with was flow cytometry to look for HLA antibodies. But at the end, we have the Luminex, which has helped a lot us to allocate patients based on the humoral presentation and to follow, and especially to follow up patients after transplantation. And here is, thanks to this kind of methodologies, we could start with our PATHI program for hypersensitized patients, a program that has been presented yesterday in many talks, and I'm not going to go further on this issue, but you can clearly see here how it is going well. And this is in part because we started with a software program that we share in Spain and is able to do things at the moment and to select our patients. Okay. And the Luminex and the use of MFA and the programs we have, and that's the tools we have just to delist our patients when they have a very high level of virtual PRA. Okay, and this is what we use at our hospital, and you can see that some of the patients can decrease the PRA if we delist them and we change the intensities, and some of them in green were able to be transplanted, okay? But some others that doesn't change or they don't have offers. And this is when we go ahead with the listing strategy, okay? We are looking for the listing one. no, very few patients in the listing 2 in which we use applet mismatch, applet antibodies reacting with the applets and looking for the applet mismatch, and also the listing 3. This is very crucial, and this is what is changing also the opportunity for these patients, those that are in the hypersensitization exchange program and they don't find a donor. We are using it, and we are using in 2 conditions: never HLA antibodies fixing complement, and never prior HLA type donor type in a prior transplantation. Well, this is right. But for this, and when we are moving into the listing 2 and the listing 3 level, we have the problem that we have to interpret the applet mismatch. You know, we were talking yesterday about the epitope and also the applet. Applet is more complicated to allocate, and the thing we have some tools, some algorithms we are using, HLA Matchmaker and also the HLA EMA, both for humoral sensitization at the applet level, but also we use PIRCH to study the T-cell allo response at the applet level. We have this, but really, when you have patients in your waiting list and you have to use these tools, it takes a lot of time. It is complicated. So in our lab, other people better than me in computers, using statistics and this kind of issues, they develop this web page, which is very easy, but it is very practical in clinical routine. We combine our HLA typing. You can see here, the listing 1, the listing 2 and 3, and we are able to enter the HLA typing from our recipients and prior donors, and then the system connects to the applet registry, and immediately it takes the applet assigned to each HLA. In this way, we are able to. Oh, sorry, I don't have here the slide, but we are able also to, after entering the applets, we are able to find the applet mismatch level for the actual donor. In case we have a donor, we are able to detect the applet mismatches, and it helps a lot because it is, let's say, very fast in the clinical use. Okay, this is a kind of thing. What is important is the HLA antibodies and humoral rejection has become to stay with us. Many of the talks in this Congress are about humoral rejection, and this is even more important when the iBox enter into a scenario. iBox, which is a FDA and EMA clear product, can help to predict and has a very nice statistics, as you can see here, 0.85, which is very good to discriminate. But the thing is that the iBox has a very important component on humoral rejection, both from the serological data, HLA antibodies, but both from the histological data, because many of them are humoral rejection. Okay, and it can discriminate well. But here you see in the left corner that the classical dogma was the study of antibodies, as I have been explaining, okay? And now you have the iBox. The problem with the iBox is that it missed some of the patients that they are DSA negative. Even you don't find sometimes C4D positive biopsies, and the problem is that they are being very well classified into boxes. It works if it is classified into boxes, but the real life, the real world is not like that. It is not easy to put into the boxes, and we need to have some other ways to monitor our patients. They are not separate boxes. And moreover, when a phenomenon is increasing and it is helping, from my point of view, to explain many of the graft losses we are having without explanation from the HLA antibodies, is the microvascular inflammation, which you can see here that points almost for the same percentage of graft loss in the long term as antibody-mediated rejection. And this is quite important. It has been stressed, especially by the group by Martin Mesa. So we have on the left the typical antibody-mediated rejection, and on the right the DS negative microvasculature inflammation, in which the loss of the graft loss is similar, and the progression is important, and it's important in the progression to transplant glomerulopathy. So we must take into account this kind of issues, and let's say when we implement digital tools in our practice, we must to think in some of the things that not only HLA antibodies. Because, as I told you, the iBox is good enough, but we cannot separate so well different diagnoses. And we must to find a digital tool able to look in the middle of this on the progression from one box to another one. And it could be so important. We use digital tools and we forget the iBox, because the other problem, the important problem with the iBox is that it is a biopsy. And so we have to be invasive, and this is not so easy to do in the post-transplant follow-up. Here you see some of the tools we are using in the pre-transplant, mostly HLA high resolution and also preformed DSA antibodies. Some of the tools, as Dory has shown, and probably will help to select the patients. And then we are studying a number of post-transplant biomarkers like cell types, phenotype, cell function, ELISpot has been talked today also about it, pharmacokinetics, torquetinovirus, which can help to monitor immunosuppression, and some others like extracellular vesicles, transcriptomics, microRNAs, and the cell-free DNA. And the cell-free DNA has been a very nice tool able to diagnose, okay, or is used to diagnose, let's say, graft injury, okay, most of it based on due to antibody mediated, but not only. And the area under the curve has been is very nice and has been demonstrated by the multicenter Catalan study, which is really nice data. And also we have demonstrated it in our unicenter study in Valdecilla. But the point is that cell-free DNA has demonstrated to have a very clear negative predictive value. But what about positive predictive value? It is not so high. So if it is positive, not always it doesn't correlate with the biopsy. Okay, it doesn't correlate. But is it saying us something about the graft outcome? We are looking for it. We dismiss it and forget it. Okay, I must tell you. It could be a passive marker, or we can introduce it in the new model and in our new digital tool. And although the low positive predictive value, think about it as a danger-associated molecular pattern. And it's possible that the positive result we are finding is a stimulus to stimulate well-tolerant receptors in the surface, or well to stimulate inflammation, and to induce some kind of inflammation through the innate immune system that is able to stimulate the adaptive response also. But it is a low-grade, it could be a kind or a source of low-grade inflammation when we find it. And it doesn't necessarily mean histological rejection. Let's say this. It could be like an iceberg. We have the typical clinical rejection, and down the iceberg we can have the production of cell-free DNA that is stimulating the innate immune system, is priming the innate immune system, subsequently is activating macrophage and also another innate immune cells, and inducing somehow the microvasculature inflammation, and could be one of the sources. So when we are looking for the cell-free DNA as a tool to monitor after transplantation, think on it in this way. Also the complement is curious, but the complement is still the forgotten actor into transplantation. Now most of you are nephrologists and you are looking for complement in primary glomerulopathies, and you are using complement inhibitors in glomerulopathies. Okay, we know the complement with the three arms, the classical, the lectin pathway, and the alternative loop. Okay, finally production the membrane attack complex. Could be complement responsible of the long-term low survival, or let's say not so good survival plateau after 5 years? Why not? It could be. So there are 3 arms, okay? And we are always thinking, when we look at complement transplantation, we are looking at the antibodies that are fixing complement and nothing else. Okay. Once we start with the transplantation, we have the ischemia, the injury reperfusion, the ischemia reperfusion injury. This is a kind of activation of the complement through the lectin pathways. Why? Because we are exposing carbohydrates. And this is a way of activating lectin. And it is very clear when you compare recipients, living donors against DCD donors, you can find that there are differences in the expression of complement activators. It could be a source of complement that could be doing something there. For sure, in the middle, we have the antibody-mediated reaction, classical activation, and at the end, also, when we activate the complement through any of the 3 arms, we have the production of C3A and C5A, against, among others. They are anaphyloctoxins, but they are also chemokines that are able to attract a number of leukocytes, a number of inflammatory cells to the graft, and induce this kind of inflammation after transplantation. So, this is another, from my point of view, from immunological point of view, I think we must consider it. Furthermore, when there are another actors in the complement, which is the complosome. I don't know if you have heard about it. It's a new concept in immunology. It's a non-canonical pathway of complement activation. It is activated intracellular in any cell. Complement normally is produced by the liver, and indicates inflammatory systemic is a marker of systemic inflammation, but also within the cells, it can be produced by any cells. It is activated by a number of enzymes, and the levels are not so important, and probably we are not able to detect it in a serum assay. But at the intracellular level, they are working. And on the right, you can see, and you can read this review from Nature Review Nephrology, very nice review, in which they show the cases in which complosome has been involved. In red, you have some diseases, and for instance, kidney fibrosis has been involved. There is no evidences in transplantation yet, but who knows in the next feature. And moreover, when you are looking for new therapeutics, and one of the new drugs we are thinking on inflammatory diseases are immune metabolism drugs. So if you are able to modulate the cellular immune metabolism, you can go on therapeutics, and perhaps you must start looking at the complosome. Post-transplant monitoring, for sure, transcriptomics. There is a lot of literature about transcriptomics. The first 2 lines, you have the bulk transcriptomics or the single-cell transcriptomics, RNA. Okay, they are good. They are good in research and giving you ideas, but they have not demonstrated any clinical value yet. Probably because they are not spatial. They don't have spatial information. They can have in the single, they can have cellular information, but not spatial. We could look for transcriptomic or proteomics at the spatial level. There are new tools, there are new methods, and probably we will see them in the next year. At this moment, they are so expensive, and they are only for research use. But as I told you in the beginning, we started with Terasaki in the 2008. Then we didn't use Luminex, and nowadays we are very expert in Luminex, almost 15 years after. It is probably that tools like Dory has explained, with combining with this kind of markers, we can use them in 5 years' time. Just to go ahead, another important point, when we use tools, immune tools, we must use them as companion diagnostics. We are starting with clinical trials, but we are not using these tools just to decide what drug to use in our clinical routine. I guess that the tools we are thinking on implement, and the algorithms and the digital tools we will use, they will look for their use as companion diagnostics, which is quite important, and not many drugs are used in such a way, although it is important. And on the right, I explained you the problem we have with the development and validation of any tool, any a method we are implementing in our monitoring. We must validate them in the clinic, and it takes a lot of time and a lot of multi-center studies. Just to finish as a conclusion, we have the traditional view with the serum creatinine, the proteinuria, okay, the biopsy, and these kind of things, but that's the old and the reactive way of action we have in transplantation. What we are proposing in the middle is the iBox model. The problem is it is so invasive, but it has demonstrated to be very used. And we have to use a multimodal dynamic prediction engine. We have to try to develop this kind of tool just to use in the post-transplant monitoring to be effective, and more especially to be preemptive, to be before the damage is there and be able to use the drugs that are able to stop this, and for sure to make the lower damage as possible, because drugs also do damage in the tissue because it's an immunological battle, and this is bad for the organ. And thank you so much. Sorry for the time.
Yeah, please.
Thank you so much.
Come here. Thank you very much for this very interesting presentation as well. Again, we will do the discussion at the end. And now it's my pleasure to introduce to you Stefan Schneeberger. Professor Stefan Schneeberger, he is the head of the surgery clinic at the Innsbruck University. And we will hear about advances in ex vivo organ management. So please, Stefan, go ahead. And happy to have you here, at least online.
Thank you, Fritz. Thank you, Daniel. I hope you can hear me well.
Yes.
Maybe you can give me some confirmation.
Yes, we can.
So thanks to the organizers to invite me to this session. Sorry that I cannot be there in person. I was asked to talk about the advances in organ machine preservation techniques and functional assessment, and then current and future applications. Here are my disclosures. So before we dive in, I always find it helpful to recalibrate and think of, why do we engage in machine preservation? What are the actual goals? And I think they're sort of twofold. First, we want to address the mechanisms of ischemia and perfusion injury and ameliorate the effects so that they can be, divided by the impact on the bioenergetic function, mostly related to the viability function and intactness of mitochondria. So stabilizing that is one goal, and through this to interfere with the inflammatory response that otherwise follows are sort of the principal targets of preservation or better preservation, because they have clinical implications. Prolonged cold storage does relate to inferior graft survival, patient survival, and in kidney it also increases the risk for delayed graft function. The other fact in this context is that, driven by at the time limitations, we inherently make bad decisions as humans in the allocation process, and we're pathologically incapable, I would say, to make such good decisions, except maybe for Dory, who can calculate all the factors and make informed good decisions. But I guess we need tools, as described by Dory, AI-driven tools that help us to better determine which of these parameters that organs come with really predict the outcome. Again, the decision-making currently applied is flawed, and it's knowingly flawed, and it leads to a high discard rate, as shown to the left. So we looked at the discard rates in Eurotransplant in our area and in the United States, and I think those are impressive numbers. If we look at the past 10 years, in Eurotransplant, 32,000 organs, and in the US, 332,000 organs were discarded while being available for transplantation. So this is clearly a large resource of organs next to xenotransplantation, probably the biggest hope to close the gap between need and availability. And this is just to illustrate that the human factor doesn't help. We tend to reject organs more on the weekends and more during later times of the day. So it's clearly driven by a bias that results from human behavior. It results in also problems that are generated through the lack of time. We jump to patients that are further down the line in the waiting list, and that creates an inequity and an unbalance in the actual, real, true best allocation of these organs, as illustrated by the out-of-sequence allocation in the US. So much of it relates to time, and that's why we felt time is of essence. If we could just change the fact that we don't have time available in transplantation, maybe we can change a lot of things in this field. We can maybe prevent injury through better preservation techniques, allow organ assessments, and then eventually advance and do organ repair and immune modification and gene therapies. So which are the techniques available currently? And then I'll advance to sort of newer things in this field. It's important to emphasize that machine preservation is not just one entity. It starts with NRP, followed by cold storage, back table preparation, followed by maybe cold storage, and then hypothermic oxygenated machine perfusion with or without oxygenated rewarming, plus or minus NMP. So and that makes it a little harder to dissect and interpret. It's not one entity. Different centers use machines in very different ways. And it's important to emphasize that we need to identify the individual benefits of all these techniques so that we eventually figure out sort of which sequence is best. In addition, and on top of this, there's hypothermic preservation technologies that are advancing, and I believe especially supercooling will enter early clinical trials in the next year. So this may also be helpful in terms of the storage of these organs prior to preservation. If we look at the market in the past decade, a lot of devices came to the market, have been advancing or are advancing to become available. I would differentiate maybe between perfusion devices that are a little simpler with simple pumps and oxygenators, and then preservation devices that are emerging that come with more and more advanced and sophisticated feedback loops that do a better job in keeping the equilibrium for organs. That's especially relevant for kidney, and I'm showing 3 examples of the Metra-K, the Ebers device, and a newer device from the US that we call POD, perfusion oxygenation device, that have more advanced feedback loops and have the ability to preserve kidneys for longer periods of time. So that's the hardware, and then we also need the preservation recipe in addition to that. I'm showing you the example of the preclinical testing that we did for the development of this device. Again, with the US company, we've advanced and integrated, I believe, key functions and features into this device, such as a very low hemolysis pump, a feedback loop for pressure flow, oxygenation, pH, CO2 control, glucose, integrated cameras. It's all cloud-based, so you can monitor that, a moisture management system. And so with that and with the application, we managed to advance and extend kidney preservation now to about 4 days, 118 hours, and the histology at day 4 really looks good. The kidney is functioning and seems to be happy and healthy. So that's one side of the coin. The second important element of these are the preservation solutions. Cold storage solutions have been investigated, but there has not been so much advancement with respect to the ingredients added to the preservation solutions that are used in clinics. And the same applies for NMP solutions. They're mostly blood-based with buffers and vasodilators, anticoagulants, antimicrobial substances, bile salts, etc. But they're still, I would say, in an early phase of development, and certainly we'll see much more emerging in this field of the recipe of preservation solutions in the future. Now, with respect to functional assessment, I'll start with hypothermic oxygenated machine preservation. I believe Philip Dudkovsky and his colleagues have established the factor of FMN as a biomarker that indicates the bioenergetic condition of livers. And he and others have shown that this correlates quite nicely with the early outcome of the liver transplantation. So this can serve as a biomarker during HOPE. If you look at the rate of anastomotic, non-anastomotic strictures, however, I think you see the numerical difference and the p-value, but also that the individual data points still make it hard to determine which of these organs will in the future have an non-anastomotic stricture. Now, in NMP, you have a larger scope of tissue and samples available from the perfusate to the bile to the appearance to tissue sampling. Some early examples of how this can help to predict the outcome is, for example, the lactate area under the curve, where we have shown with centers in the UK and Germany that this has a relatively good predictive value, especially if you take the later hours during the NMP process. And if you take all these data points, it is helpful to say, I would say if it's not degraded, if lactate stays high, then it's a warning signal. This applies to bioenergetic profiling. If you look at mitochondrial respiration, pyruvate lactate, for example, efficacy or cytochrome C control, and monitor this over the course of NMP, you find that this would correlate with early outcome parameters such as the Algraft score, and this corresponds with the mitochondrial damages illustrated by the imaging shown in the top panel. Another thing that we looked at is the inflammatory response during NMP, and you see basically a lot going on. I highlighted interleukin-6 expression because we found it to be clinically relevant. So you see some of these organs are undergoing a very strong inflammatory response, and this is important because basically it describes the biological performance, but also because the high load of interleukin-6 can really result in disturbances, hemodynamic disturbances, when you connect the livers. And we've seen cases of, basically a shock response and the need for resuscitation if you connect the liver with very, very high loads of interleukin-6. So it's a warning signal. It doesn't say that these livers would be bad. It's just saying that they undergo a very strong inflammatory response. Another example of assessment shown here, the imaging techniques illustrate the perfusion quality in livers, and this can be done for kidneys also. So this can be quantified and translated into a sort of a quantitative assessment over time of the perfusion quality in the cortex of the liver, as shown in this example. And if a system is trained to then analyze the bile ducts out of this picture, we can assess the perfusion quality of the bile duct, and this seems to correspond with the outcome after transplantation in terms of the bile duct complication rate. As mentioned, the gene expression analysis is an interesting tool for research. This is certainly in a preclinical phase. It helps to understand the inflammatory response that is going on in these organs, and we identified the early activation of neutrophils, for example, in livers, and how they being activated and start being mobilized and transition to the perfusate, and then change their phenotypic profile to become more of a resting and regenerative state, while Kupffer cells are activated at a later stage. These data can be transferred into a gene panel that would mathematically then predict the fate of these organs, and this set of 7 genes has corresponded with later transplantation or discard. As an example, this is all in the preclinical phase, and it needs to be validated by others before this can be used as prediction functions in the future. So what are the advancement and novel applications? HOPE is being extended. That's from the Groningen group, where they extend HOPE to up to 31 hours of total preservation times. However, the average time was 10.2 hours. They try to avoid nighttime procedures as shown in this graphic. It's not just extended HOPE, but it can be extended HOPE followed by COR and NMP, and then daytime transplants. So there's some element of assessment of these organs, but they did manage to avoid nighttime hours, and I believe that this is an advantage. It's not always easy to measure how much these values, but it is clearly in our experience also. This is from our program. We've now done 516 NMP cases. We've done an additional 168 transplants on organs that we would have otherwise discarded. We have a high ECD rate of 81%, and we put these organs into complicated recipients, 60% on non-benchmarking. We've extended clinical liver preservation up to 48 hours. And in 44 cases, we've extended it to beyond 24 hours. We routinely do assessment of quality of function. We don't do them at nighttime any longer. And we do simple treatments such as specific, donor-specific infectious assessment or treatment. Assessment of donor malignancy, not always do you have otherwise the time to wait for the results to come back, and then await, for example, also the outcome of a donor trauma. So that's how we can assess organs that were deemed non-transplantable and see if they really are. The outcome in a nutshell are that by using this, we can transplant more marginal livers with the same outcome as compared to a control group. Now, I told you that we've extended the time more recently and included 44 cases where we've extended it beyond 24 hours with the same results. And this has increased over time. So lately it has become 20% of our livers that we extend beyond 24 hours. That resulted from a preclinical work where we've tested liver preservation for 1 week, and we've developed a protocol, a perfusion protocol that allows us to do that. We've also identified risk factors for that. So now we do know that the early bioenergetic performance predicts the outcome after 1 week, and we can use this to assess livers and say that we can extend or not the preservation time in these livers, and also develop the protocol. Liver splitting is becoming popular. This is from Washington University, an example where they split the liver for a pediatric recipient during NMP. In this case, they only used the left graft, unfortunately not the right one. It didn't apparently find the recipient. We took a different approach, and now we have an N of 3 of these procedures, where when we receive the liver, we put it on an NMP. It's mostly because they're received at late hours, and we don't want to do pediatric transplants in the night. We perfuse them overnight, and then we take them off the pumps and we split them. We do the pediatric transplant this second day. We put the second half back on the NMP, perfuse it for another day, and then do the second transplant the day after. This is to make it daytime procedures and to have your A teams available. And by doing this, we extend the preservation times to 48 hours. We've done 6 of those, and all 6 grafts have survived well with very good outcomes. What else is there out in the literature that's new? Permanent NMP and graft survival seems to indicate, that's an assessment from the US in 373 NMP livers, that the survival curve, the cumulative survival, is significantly superior to SCS in these livers. When investigators compared back to base NMP with in-transit NMP, there doesn't seem to be a difference. There's a slight bias in this assessment because in the NMP group, they only included, in the back to base NMP group, they included livers with 10 hours of cold storage or more only, but still they seem to be doing well. What to await for the near future? The outcome of this study will be interesting, the DFAT study, where they take steatotic livers and apply a defatting cocktail to see if that would degrade the fat content and maybe stabilize or improve the outcome. Another preclinical example from Hanna Essa is a senolytic agent that is applied to stabilize and improve cholangiocytes. So that could be an interesting tool to improve the outcome, the bile outcome after liver transplantation. Again, this is still preclinical. I find this a fascinating example from Fotis Sampatziotis, where he took the liver that he removed from a Minji patient and then gene treated in 1/2 of this liver over a course of a week. Thymidine phosphorylase deficiency effectively, and showed a gene and protein production. So this is an early example of an AAV-based gene therapy ex vivo in a splitted liver. Now, kidneys is a slightly different animal. It's a little harder to preserve kidneys for prolonged periods of time. So first thing we did is look at the actual features of the damage, and we find after 24 hours good preservation, good flow and resistance parameters, but vacuolization and membrane thickening and changes and swelling of the mitochondria indicating progressive damage with conventional devices. Innovations come from John Ruveling's group, but also from Tobias Huber group from Hamburg. They have assessed 2 neuropreservation solutions for subnomothermic kidney preservation for 4 days. This seems to improve the preservation and the condition of these kidneys at day 4 or later. And the Hamburg group has transplanted these kidneys in rats and found superior survival. So this needs to be tested still in large animal models and clinical testing, but there might be a space for hypothermic or subnomothermic kidney preservation and the ability to prolong this through adopting the recipes for the preservation solution. An exciting example, I believe, is emerging from 34 Lives, an Indiana-based institution that takes kidneys that have been sort of hard to place or discarded and perfuses them subnomothermically for 2 hours and then ships them with oxygenated hypothermic machine preservation to the recipient center. They've done 104 cases, transplanted 94 with basically good outcomes and lower DGF rates compared to the control groups. Cytokine absorption and treatment is an interesting concept and is now being assessed in this clinical trial. This again is just a trial protocol, so we're awaiting the outcome to see if cytokine absorption in kidney preservation has an effect on the early outcomes, specifically delayed graft function and early rejections. Blood conversion has been shown by the Cambridge group to be feasible, and protein splicing certainly is an interesting aspect in terms of the blood group, but maybe also HLA masking and modifications. Mitochondria-targeted therapies such as MitoQ, it stabilizes mitochondrial membranes, has shown a promising preclinical result in ex vivo preservation platforms. Mitochondrial transplantation, again, preclinical has shown some promising results with respect to better viability and less apoptosis in mouse and pig kidneys. Still, however, I believe that T24 outcome histology doesn't look superb, so we'll see how this translates into advanced preclinical testing and then clinical trials. A number of papers, I didn't list them, is investigating the cell treatment in kidneys and other organs ex vivo. This, but also organoid therapy, as shown in a later study from Spain, where Nuria Montserrat, together with Henry Luvenick, showed again an effect in a preclinical study of placing organoids in kidneys during normothermic kidney preservation. We'll see what emerges from then, which are the actual real benefits for patients of such cell therapy strategies. I'm summarizing it in this slide that I took from Andreas Schleger's publication, which summarizes basically the disciplines of NMP and HOPE and how they individually can help to increase acceptance, improve preservation, maybe serve other tools such as gene therapy in combination with xenotransplantation, or by establishing and improving organ viability, and serves as the platform for additional treatments, including those that I had just mentioned, but also many more that I didn't have time to go into. So with that, I'm closing. I'm thankful to be participating from the distance to this great meeting. Thank you.
Thank you.
Thank you so much. So now we open the discussion, and you can go to the microphones if you want to ask some questions.
Well, important to come to the microphone because we are recording, and otherwise Stefan probably won't be able to hear it. And
yes. Sorry, I am a speaker, but I have a question because there is nobody in the room at the moment. Just to start for Stefan. Okay, you are proposing to use analytics in your system. Okay, there is one of the issues, and but this is somehow let's say an anti-inflammatory approach. What about using lipoxins or resolvins. Have you heard about that? Because they are supposed to be contra-inflammatory drugs, and let's say it will be even less, it will induce less damage than other anti-inflammatory drugs you are proposing.
Right. So I don't know the specific data that you're referring to. However, I believe that much of the interventions that are being attempted, they channel through an anti-inflammatory response directly or indirectly. The big unknown, I believe, at current is how much and which type and how specific such an anti-inflammatory intervention needs to be. Is it as basic as a cytokine washout or filtering? Is it more specific than that? Is antisenescence drugs, as you say, just a factor or another pathway to act through anti-inflammatory modalities? All of these things, I believe, are unknown. I personally think that it's not going to be as easy as just filtering cytokines and be sort of unselective with this. It reminds me of the interventions that we've seen in other inflammatory diseases or components of that, such as myocardial infarction, where basic abrogation of the inflammatory response was not the solution. So maybe the same applies here, and we'll need to sort much better which part of the inflammatory response is beneficial and which is not, and then isolate that out and be more specific with the anti-inflammatory treatment. So I hope that's helpful as a response.
Questions from the audience? Dr. Revuelta?
Thank you, Revuelta from Hospital Clinic Barcelona. Thank you for all of the presentation, very inspiring to all of us. I want to ask to Dori about, I have the opportunity to review the new European Artificial Intelligence Law, and then one of the things that all the clinical decision-making tool that we are now designing to try to integrate in a hospital network is considered like a medical device. And in terms of regulation, how you are faced to try to combine all these technology, these tools, to integrate in the hospital in this kind of regulation in the States? Thank you.
Yeah, great question. So there are two issues, I think, with the use of these tools in clinical medicine. The first one's relatively simple, but not so simple, which is that we cannot let them, we as clinicians, cannot let these tools make decisions for us. We have to use these tools as partners, because no matter how much regulation we put, there will be instances where these tools get it wrong. And we need to be, as clinicians, looking at what the tools are saying and thinking, that doesn't make sense. That doesn't align with what I'm seeing. I'm going to ignore the tool and I'm going to use my own clinical judgment. And I think that for many years to come, our clinical judgment will still carry a tremendous amount of importance in all of this clinical decision making, and the best an AI tool will be able to be is a partner. And again, I mentioned this very briefly in my lecture. Think about the radiologists and CT scans and MRIs. They get a tremendous amount of information from the AI that is looking at the images, but ultimately connecting this to the clinical scenario, using the judgment that they've had, the art of medicine, because there's a lot in the art of medicine that can't be quantified in the science of medicine. So that's, for us, as people who take care of patients, probably the most important thing to keep in mind. For regulators, for them, it's very important to keep in mind that right now, I think there are some million tools available out there, almost none of which have been through peer review, right? And this is really scary. And some of which are available for our patients that they use without consulting with us, and a lot of which are trying to become integrated into healthcare systems. And validation is extremely important. You've heard a lot about iBox. The amount of work that Alex Lupi has put into validating iBox, in French cohorts, international cohorts, cohorts over time, et cetera. All of that validation is critically important for these tools. And it's important for regulators to figure out what is going to be considered a reasonable amount of validation at the time of approval, and then also following this over time. Because what happens with a lot of these tools is they embed biases that start, and if we don't continue surveillance of these tools, those biases will persist even after a time which we realize those things are wrong. And so not only validation at the time of approval, but continued surveillance, continued monitoring for performance, for biases, et cetera, is going to be critically important as well.
You have another question?
Hi, Oriol Bestar, Hospital Vallebron, Barcelona. Great talks. I really enjoyed all of them. I have just a question related to what you were saying, Doris, and I mean, for everybody. So I think it's clear that, I don't know if it's a promising or it's just a reality. I don't know how long it's going to take to have as a companion tool these new AI decision supportive tools, whatever we want to call them. But my question is beyond that in terms of advancing the field. So in terms of having these tools to have hypothesis generating data, and especially which can give us, new graph trajectories, new patient phenotypes. So my question is, how trustable are them in a field that the mechanisms are pretty much not that well known? And how we reconcile this? Right? So how can we trust these fantastic and fast data generating hypotheses with a field that eventually, so the mechanisms are still pretty much unknown? I'd like to know your...
Yeah, I can start and then let others comment as well. I think to me, the answer is embedded in your question. So I think one of the beautiful things about the interaction, remember I said clinicians need to be partners with AI on the clinical decision-making side. On the science side, scientists need to be partners with AI. And one of the really beautiful things is that AI can pull from a huge amount of data these patterns and then say to us, this pattern is happening. I don't know exactly why it's happening. AI can't know why it's happening, but AI can tell you that it is happening. And then we take those patterns into the lab and we do the more traditional science. So in the same way that I would tell you clinical medicine is not going to disappear and be replaced by AI, I would also tell you that more traditional scientific approaches are not going to disappear and be replaced by AI, but they're going to be guided in sort of this partnership. And so, AI might give you 5 ideas, might say, I've identified these 5 patterns, and then you're going to go prioritize based on what makes sense sort of more mechanistically for you. But AI can do really cool things. So for example, you're probably aware that a couple of years ago, AI scanned 1 trillion proteins available and identified one that could be a very good antibiotic. And this antibiotic was named Halicin. Do you know why it was named Halicin? Hal was the computer in 2001: A Space Odyssey. And so they named this antibiotic after that very first computer. But again, it can identify these things, but when that was identified, then that was taken into clinical trials. And obviously it's a simple example, but nobody's going to use an antibiotic that AI identified without actually testing it in multi-phase clinical trials. And I think we need to think about that same perspective when thinking about AI science interactions.
My point would be that the things we are talking today is not only the machine learning, the neural networks, but the quality of data. I am engaged in a population-based cohort, 51,000 population, and our problem is interoperability of the data and how we get non-structured data. Because in transplantation, there is only a few structured data that you can use in your big data analysis. But what about non-structured? What about what the clinician is writing in their papers and you are not able to extract? So I wonder if there is any automatic machine, anything just to accelerate the supervision of the quality of data. You know something about that? Because for me, that's the bottleneck at this moment. Until we don't solve this, I get big data could not be a reality.
Yeah, I think the unstructured data is a really important point. I mentioned some unstructured data which comes in the form of images, but also unstructured data that comes in the form of words or a lot of calculations that come out of the HLA lab or something like that. A few years ago, the early versions of natural language processing were explored to convert unstructured data into structured data. So for example, to take the rambling that I do in my operative note and to pull from it, oh, this is how we did the anastomosis, right? I think the newer era of natural language processing using large language models is proving a lot more effective in that. And I think that we will see that we can harness some of these AI tools to convert our unstructured data into structured data to make our predictions even better. So that's what I would say about that.
I would like to shift gears for a minute and ask Stefan.
Thank you.
You've presented some incredible data about the ex vivo management, and you were leading a big surgical department. You have quite some resources, I understand, and but I understand also that we're just at the beginning of ex vivo organ management. So what do you think? How will this be organized in 10 years once this has come to a real clinical level, and you're having the 3, 4, 5 organs? During some days you're doing not only diagnostics on those organs, you're doing therapies on those organs. Will a surgical department, will a hospital still have the resources and the organizational capacities to do this, or will you have to take this beyond? Will this be industry? And also, maybe how can Marcos and Dori help you in that?
Very good question. Thank you, Fritz. I believe that it will no longer be the academic environment or the hospital environment that will be the right place to do that. We see examples of that emerging. Maybe in the US, we have one example. Transmedics is taking it as an industry to transport and work as a logistics company. OPOs are considering engaging in this task and serving as organ preservation centers. We have in the UK, I guess, 5 designated ARCs, as they call them. It's a national program where they want to establish such hubs throughout the country in order to serve in such capacity to collect, assess, and then monitor and manage these organs. In Austria, as you said, we've advanced this center and worked on this for the past 7 years. And just yesterday, we have received approval to spin off from that and create an LSC, because we believe it should advance and expand beyond the immediate academic environment, because over shorter or longer, it gets this more industrial spin and commercial element to this. I hope that it will be in strong ties and connections with the academic community and the medical community, to be driven by the right causes and influenced by the right factors. So that's my hope, that there's going to be national, international programs that will help and centralize this. An important element, as mentioned during the presentation and also by you, is that tools such as the ones described by Dori are essential, I believe, to guide and navigate this process. I personally believe that the entire allocation system will change almost entirely once this has advanced to become a clinical routine and be established as a concept more broadly. And then we'll see probably a lot of things changing over time that refers to the foundation of the allocation, the parameters that are used, the logistics and the directions of travel and the distance of travel. Maybe this can become more international, and an international exchange can result from that. Those are, I guess, goals that are further away in the future. So it's going to be not sort of a single step, but a multi-step process that will keep advancing and changing. And hopefully, this will help to close the gap between supply and demand in organs, and also improving better outcomes because of better allocation.
I think that's a very good outlook, but I believe, I'm convinced, and I fear that we will have to learn a lot and have to be able to adapt to change in a very short time. So I think we have 2 more minutes, 1 more minute.
1 more minute. I have a question for Dr. Seguer. So, do you think, you hear me? Can AI help reduce inequities in organ allocation and access to transplantation? The AI systems can reduce the inequities in allocation.
Yeah, I mean,
Because the data you're using.
so I think the simple answer is yes. AI can tell us where we're going wrong through unsupervised views of everything that's happening. There's actually an interesting article, I think JAMA or New England Journal, that looked at, like, we know that large language models are biased, right? And it looked at not just looking at the biases of the large language model and trying to fix them, but looking at the biases and saying, that's telling us something about ourselves. Maybe also let's try to fix us. So I would say that these tools can tell us where the inequities are coming from, and we can use mathematical tools to tell us how to fix the inequities. But anyone who has been watching from the stadium, what has happened in the US and organ allocation in both kidney and liver and everything else that we're doing to reduce inequities can see that we are the limiting factor in reducing these equities. We need to decide that what the math is telling us to do is the right thing to do, and we need to implement those things, and we need to implement them in a way that's clinically reasonable also.
Okay. And just to close, if we meet again in 10 years, what aspects of transplantation you think will look different for all of the 3 panelists? And we close.
I don't know exactly that. What is sure that we are going very fast, okay, and things that I was talking about antibody-mediated rejection. It has changed in 15 years, absolutely. And the number of tools we are employing today, those that Stefan has explained, those that do artificial intelligence we are implementing, and it will accelerate. For sure, we will have results even in 5 years. And look for iBox. Started and now it is approved, and so it will go very fast for sure. I don't know exactly what. From immunological point of view, cell-free DNA for sure, okay, with HLA antibodies, some, let's say, cell subsets that can help, and we'll see.
I'll go next so that Stefan has the last word. I'm going to flip your question and say, what won't change? I think we're going to be surrounded by data, surrounded by tools, surrounded by new, cool, weird, innovative things, better ways to use things, but we are still going to have an organ shortage. We're still going to have inequities in the system, and we're still going to be fighting over who gets saved and who doesn't get saved. And I think that the better we can build systems for deciding these things that make all of it in a way that makes us comfortable, the better we're going to be in the future.
Stefan, one last word.
I wish I had a different perspective, but I'm afraid that what Doris said aligns with what I think will happen. We'll have inequity and an imperfect world still in 10 years. I believe that, however, the differences between regions will be greater than they are today. Regions and areas that are doing better and have managed to close the gap, and other areas where it's still wide open. And there's another concern, maybe indirectly related to what we're talking about, and that is the economic future and health economic challenges that we are facing currently, and certainly even more so in the future, especially in Europe. We struggle with keeping up today. We'll struggle more with keeping up with innovative technologies in the near future. And I'm afraid that sort of the global economic development will come to hunt us and maybe hamper the advancement and development of the tools we've been talking about.
So we don't have more time. So thank you to all the speakers for your excellent talks and inspiring talks. And thank you all for coming here, and welcome again to La Coruña. I hope all of you enjoy the city and the rest of the Congress.
Thank you for that.